Thank you very much. Good afternoon, everyone. Thank you for being here, and thank you to the organizers for giving me this stage. The topic we're going to look at today is iOS application penetration testing, and more specifically, how we can make it less painful than it usually is. So let's get started. A quick word about me before we get into the technical content. My name is Khayal Farzaliyev. I'm the founder of my Pentesting boutique called Shaman Red Team. I am a penetration tester and an AppSec engineer, which means I spend a lot of time penetration testing applications and helping developers to make sure that I can't break into their applications. Outside of that, I am a PhD student and a lecturer, so I also spend some time teaching. And the topics I care about most are web mobile app hacking and secure design and software development, and a bit of cryptography and Internet of Things security. So here's the agenda for today's talk. First, I want to talk about the challenges that makes iOS pen testing difficult. Then we'll go through some iOS app basics. After all, we will talk about jailbreaking, what it is, why we care about it. Then we will get to the security model of iOS, the attack surface. We focus on during audits and the difference between static and dynamic analysis. And we will talk about how to sideload iOS apps onto our own iOS devices. We will see how to use dynamic instrumentation methods, and we will have a short demo at the end. So let's get started. So let me begin with my story, how I ended up diving into this research in the first place. Here is how it began. I spent weeks hunting for a jailbreakable device that was actually in a good condition and usable for testing. And when I finally found one, it felt like a victory, really. But until I realized that its iOS version was lower than what my target app required as minimum. And simply the app simply refused to install. And naturally, I wasn't about to give up my jailbreak, so I made developers suffer a little bit by tweaking the application so that it works on the lower iOS version. And surprisingly, it worked for a couple of weeks. And then things went wrong again. I forgot the passcode on my device, and the only solution was a full reset, which means updating to the latest iOS version and saying goodbye to the jailbreak. So there I was, no jailbreak, a newer iOS version that had no jailbreak available, public jailbreak, and my target app I still needed to test, and my deadline. And that's the time where I had two choices. I could either give up or figure out how to do this without a jailbreak. So I chose the second one, and this is basically how this talk was born. So why does this story matter? Because every single thing I described is a common issue when it comes to iOS security audits. For example, finding a jailbreakable devices is harder every year. Recent versions of iOS don't have a public jailbreak at all. And here is the cruel twist. Some apps require a higher minimum iOS version. So even if you have a jailbroken device, the app might still refuse to install. And on top of that, jailbreak is not free. It may disable some features like biometric authentication, Face ID and Touch ID, which makes it impossible to test biometric authentication properly during a security audit. And finally, sometimes you simply do not want to jailbreak your own personal device because you may use it for day-to-day life. So the challenge is real, and the solution we are going to explore today is how do we do meaningful pen testing even when we don't have a jailbroken device and jailbreak is not an option. So before we go any deeper, let's make sure we all share the same foundation. What's an iOS app technically? iOS applications are usually written in one of two languages. The older language is Objective-C, and the newer and more common language is Swift. Developers write these apps in Xcode, which is Apple's development ecosystem, and it only runs on macOS. Once an app is built, it gets distributed through the Apple App Store, and before it can even be installed on a user's device, it must be signed with a valid Apple developer certificate. And the signing is Apple's way of saying that we know who made this app and we trust it, and at least we verified the developer. Now, on the device itself, each iOS app runs on an isolated process and operates within a strict sandbox, limiting access to other apps and system resources. And one more thing, that the app package is encrypted on disk. It can only get decrypted when the app is actually being executed. So let's talk about jailbreaking. What is it really? Why do we care about it? First of all, iOS is very different from Android in one key way. It doesn't give us a shell by default, and jailbreaking is the process of opening that door anyway. And it removes the restrictions that iOS normally enforces and gives you deep system access, essentially root-level access to the device. But jailbreaking is not something you just click a button to do. It is achievable through an actual security vulnerability on iOS devices. Once you have a jailbroken device, you can install things like custom themes, community apps, and you can have package managers like Slow allow installing community software, which wouldn't be allowed on Apple App Store. So, which devices can actually be jailbroken? The best public resource for this is this website here. And it shows us for any device and iOS combination whether there's a jailbreak available. The devices that are currently jailbreakable across all their supported versions, iOS versions, are older models. You can see them here. And this is due to the hardware level vulnerability, and that allows a jailbreak on any iOS version they can run. And for iOS version 17 and newer, which is basically every modern iOS device sold, there is no jailbreak available, at least publicly. And we can look at this table here for my iPhone XS. We can look at the jailbreak options. And we can see NA entries, which means there is no jailbreak available for the version ranges. And some version ranges can be jailbroken with specific tools. And when we have a jailbroken device, what does it actually give us? First, it lets us install unsigned IPA files. Normally, every app that runs on iOS must be signed by a trusted developer certificate. On a jailbroken device, this rule is relaxed. And so we can install apps from arbitrary sources without fighting the signing system. Second, we get root-level access to the file system. That means we can browse any app's directories, inspect their databases, look at their preference files, look at their log files, because we are simple root. Third, we can run dynamic analysis tools in their most powerful form, which we will talk in detail later in the next slides. And finally, we can install all kinds of security testing tools directly on the device. This includes proxies, debuggers, file browsers, packet capture tools, etc. All of them become installable through package managers. So jailbreaking gives us enormous power. Okay, a little bit about iOS security model. What is iOS security model actually protecting? If we take a look at the diagram on the left side, at the bottom you see the hardware level, the device key, the Apple root certificate, the crypto engine, and something called the secure enclave. The secure enclave is a separate chip, basically a tiny computer inside your phone that handles sensitive operations. Like fingerprint matching and face recognition. The main iOS kernel cannot directly read its data. It can only ask to do some operations, like if this fingerprint is correct, or sign this challenge, like this. And that operation is a very strong security boundary. Above the hardware, we have the kernel, the OS partition, and the user partition, which is encrypted. And on top of all that, each app runs inside its own sandbox, as we mentioned, and its data and resources are isolated. An app cannot, without permission, read files from other apps or access microphone or other system resources. Now a bit detailed about main security features of iOS system. App groups are a mechanism that lets multiple apps from the same developer share data in a controlled way. For example, a main app and its widget can share a common data container. From a security standpoint, if an app is a member of an app group, sensitive data might live in a shared container. Entitlements are fine-grained permissions enforced by the operating system and embedded into the app at signing time. They define what the app is allowed to do, which hardware it can access, which capabilities it can use, which groups it belongs to. Face ID and Touch ID provide biometric authentication, which is powered by the secure enclave. Our fingerprint and face model never leaves that chip. What iOS gives the app is basically a yes or no answer. Did the biometric check pass or not? So then we have keychain. Keychain is iOS secure storage mechanism for small sensitive items like passwords, tokens, encryption keys, which we also talk later in the next slides. As you see, all of this together form a layered defense. Now, faced with all that security, where do we look for problems? Fortunately, we don't need to invent this from scratch. The OS Foundation maintains a guide called the Mobile Application Security Testing Guide. You can find it in this link. And the MASTG documents around 70 security tests specifically for iOS. And they fall into these categories: storage, crypto authentication, network, platform, code resilience, and privacy. But main areas of interest during security audits, iOS security audits, are local storage of sensitive data, local authentication, including Face ID and Touch ID, platform APIs. This includes things like inter-process communications, the way apps talk to each other, or app communicates with its components. At network level, this is just backend, the APIs the app talks to. Now, before we get into the tools, let's review two famous approaches we have when auditing: static analysis versus dynamic analysis. Static analysis means looking at the app without running it. We take the IPA file, we unpack it, we look at the binary, we examine the configuration files, we search for hard-coded secrets. And the dynamic analysis means running the app and watching how it behaves. What does it write to disk? What network requests does it make? What's happening in the memory, and etc. On iOS, static analysis alone gives very limited coverage. Why? Because Swift and Objective-C binaries, after compilation and encryption, are not easy to read. You can sometimes pull out strings, some function names, some structure, but the actual business logic is buried in a machine code. So dynamic analysis is a must. Dynamic analysis is where the real insights come from. Running the app, watching it, interacting with it, and ideally hooking into it so you can see what it is actually doing, or any point in time. That's where you find the interesting bugs. In a good audit, you do both. You start with static analysis to get a map of the app, then you move on to dynamic analysis to actually test its behavior, its runtime behavior. Okay, let's continue with static analysis. We'll talk about IPA structure in this slide. An IPA is really a zip archive. You can rename it from .zip, .ipa to .zip, and you can unzip it, and you will get a folder called payload, and inside that you get an app bundle, which is another folder. The app file itself is the main binary. That's the compiled, signed machine code that actually runs when you launch the app on your iPhone device. Info.plist is the app's main configuration file. It's a structured XML document. Technically, it's in binary format, but it can be converted to XML very easily. That tells iOS everything about the app. Bundle identifier, minimum iOS version, supported devices, permissions it requests. And as a pen tester, info.plist is often the first place we read because it gives us a map of what the app is designed to do. And then we have embedded.mobile provision. It's a provisioning profile. It's basically the contract between Apple, the developer, and the device, saying this app signed with this certificate is allowed to run. It also contains the entitlement, the list of capabilities the app is allowed to use. Code signature directory is a folder that contains hash of all the files in the bundle, along with the cryptographic signature. That's what iOS uses to verify that the app hasn't been tampered with. Then we have frameworks folder and plugins. Frameworks is where any third-party libraries the app depends on are stored. And plugins are app extensions. Things like widgets inside the app, share extensions, notification extensions. They are basically little sub-apps that run inside their own processes, and they have their own binaries, their own info.plist files and signatures. Okay, now I mentioned earlier that the IPA you get from the Apple Store has an encrypted binary. If we want to do any serious static analysis, we need a decrypted copy. So how do we get one? The easiest path is to ask the developers. If you are doing an authorized audit, the development team can give you a debug build or an archive that's not encrypted. If that's not possible and you have a jailbroken device by any chance, there is a tool called Frida-iOS dump. It does exactly what the name says. It uses Frida to attach to a running app, grab the decrypted binary from memory after iOS has decrypted it for execution, and dump it to disk. This is the classic technique to getting a decrypted IPA. And if these options don't work for you, there are online services, sites like armconverter.com, decrypt.pay. These maintain libraries of already decrypted IPA files for popular App Store apps. Okay, let's say you managed to get a decrypted IPA file. The next step is to run it through a tool called MobSF, Mobile Security Framework. It is free, open source, and gives you a lot of information about the IPA file you're uploading. You have two options to use this, either self-hosted, you can clone the repository and install it and run it on your computer. And second option is to use the online version, which may be convenient for quick tests. But you, at the end of the day, upload the IPA to a third party, so consider that. So what does MobSF do? It analyzes the IPA and gives you a report with several things. It inspects the info.p list and flags suspicious configurations. It analyzes the binary and looks for weaknesses in how the code was compiled, basically binary protections. It extracts URLs and endpoints from the binary. It scans for potential sensitive strings, private keys, API keys, tokens, etc., which may accidentally left in the binary. So we are moving on to the dynamic analysis. It's the other half. For this, the app obviously has to be installed on your iOS device. We need to be able to observe how the app interacts with the system and with external services. We want to see its data storage operations, when it writes to disk, what does it write? We want to see its network communication, what requests does it send, what responses does it receive? We want to see its inter-process communication, does it talk to other apps or system services, and we want to see how it handles user input. If we have a jailbroken device, dynamic analysis becomes straightforward. We can SSH into the device as a root, we can browse any app's data directory, we can install custom tweaks and scripts that instrument the system or specific apps. But even without a jailbreak, dynamic analysis is still feasible. We can still analyze the app's sandbox. We can still trace file network operations and function calls within the app. So we came to the heart of the presentation, dynamic instrumentation. This is the core technique that makes non-jailbroken iOS pen testing possible. It's called dynamic instrumentation, and the tool we use for it called Frida. What do we want from dynamic instrumentation? Two things, basically. First, we want to capture and log application behavior in real time. When the app calls a function, say a function that reads a keychain item, we want to see that call happen, see the arguments, and see the return value. We want visibility into the black box. Second, we want to modify application logic during execution. This lets us bypass client-side security checks and test the apps as if those checks didn't exist. Frida is a very powerful tool for that. The way it works is that Frida injects a JavaScript engine into the target applications process. Once that engine is running inside the app, we can send it JavaScript code that intercepts function calls, reads memory, and modifies behavior. Now, there are two ways to use Frida on iOS. The first way is to run a Frida server on the device, and from your laptop you connect to that server and tell it which app to attach to. That's beautiful and clean, but it requires a jailbroken device. And we have another option, which is one we care most about today, is injecting a Frida gadget into the app. Frida gadget is a shared library that we embed inside the IPA. When the app launches, the gadget loads along with it, and it exposes an interface that we can connect it from outside. Because the gadget lives inside the app's own process and is signed together with the app, no jailbreak is used. And this is the key trick we have. Okay, continuing. So how do we actually put Frida gadget into an IPA? Let's walk through it. First, we need to download Frida Gadget itself. You can find it in the Frida Project's GitHub releases page. The file you want is called something like Frida Gadget version, iOS universal.dilib. Next, we need to patch the IPA. We unzip the IPA, which gives us a payload folder, and inside that the app bundle, for example, payload app.app directory, and we copy fridagadget.dilib into that folder. Now, just putting the dilib in that folder is not enough. The app's main binary doesn't know about it. It will load and ignore it. We need to modify the main binary to actually load our dilib at startup. And that is what the optool does. The command looks like this. What this command does is add a load command to the app's binary. Specifically, it adds an entry that tells the dynamic linker, when you load this app, also load fridagadget.dilib from the same directory. The executable path part is a special variable that means the directory of the main executable, and that's exactly where we copied our dilib. Once optool has done its work, the IPA is patched, but it's not yet signed, so it cannot be installed on a non-jailbroken device. So that's the next step. So sideloading is the term for installing an app on iOS device from a source other than the App Store. On a jailbroken device, you do not need to sign the app at all, as we said. You just install the raw IPA. But on a non-jailbreakable device, every app has to be signed, and that's where things get interested. To sign an iOS app yourself, you need a few things. You need an Apple developer certificate. There are two ways to get that certificate. The first way is to enroll in the Apple developer program, which costs $99 a year. And the second one is free alternative. It gives you a proper developer certificate. Also, any Apple ID you can use for that. So with your Apple ID, you generate what's called a free provisioning profile, which lets you sign apps for free. But those apps are only valid for 7 days. After 7 days, the certificate expires. The app refuses to launch, and you have to resign and reinstall. For testing, 7 days is often enough, so we can get away with that. To actually do the signing, you also need a provisioning profile, which is a file with the extension .mobile provision. The easiest way to get one is to open Xcode, create a new empty project with any bundle identifier you want. Let Xcode generate and download the provisioning profile automatically, and then grab that profile for our purposes. You may also need to modify info.plist inside the IPA. The bundle identifier might need to match your Apple developer certificate. And if the app uses app groups, you might need to update those as well. So fortunately, there are tools that can automate all this stuff for us. One of them is called Sideloadly. It's an all-in-one desktop application that runs on macOS and Windows, and it does almost everything we just described in a single interface. What Sideloadly does for you, it takes your IPA file, lets you inject custom dilibs, like our fridagadget.dilib, into it, takes your Apple ID, signs the modified IPA, and pushes it to your device over USB. One thing Sideloadly does automatically is to change the bundle identifier. When you sign with a personal or team certificate, the bundle ID has to match your team prefix, which is tied to your developer account. As you see here, it will be something like this, where the last part here is your team identifier. This is done to make sure that apps you sign do not collide with legitimately signed apps on your iOS device. So sometimes sideloaded apps can crash on launch. Sometimes it crashes partway through, and you have to debug why. The most common issues I see are the following. entitlements not defined properly. The app was originally signed with certain entitlements that your free Apple ID cannot grant. The fix is often to strip those entitlements from the entitlements plist before signing. And the plugin and framework files may not be signed properly. An IPA can contain multiple binaries, the main app plus frameworks plus plugins like widgets and extensions. Every single one of those has to be signed with valid signatures, not just the main binary. If sideloadly or any signing script miss one of them, the whole app refuses to launch, it may crash. The solution is to make sure all binaries inside this bundle get resigned. And also, finally, plist files may require manual updates. And if you want to go deeper with this one, there's a great article with Secure Labs. You may also finally consider using alternative tools like AltStore, and you may find out which one works for you and your application. So running a repacked iOS app. Let's say you managed to sideload your Frida patched IPA successfully. First, you need to enable developer mode on the device to run the app. This is a setting under privacy and security, and it requires a reboot before running the application. And you also need to go into settings, general VPN and device management, and trust your developer certificate. Obviously, the first time you install a sideloaded app, it will not be launched because iOS system doesn't trust your developer certificate yet, so you have to trust it manually. After that, you need to launch the app in debug mode from the command line. You see the exact command here. We specify our device ID and bundle ID of the sideloaded app. Then we use LLDB debugger. We use it to attach to the process by its PID. Then at this point, the app is running under the debugger, but execution is paused. You give it the continue command, and the app starts running normally, including loading your Frida gadget. And that's the moment when you can finally connect Frida to the gadget and start doing dynamic analysis. So if you want to get the detailed step-by-step guide, you can check the link from OWASP MESTG at the bottom. So attaching the Frida gadget, how to connect to the patched app. First command, we use it to list available applications on the USB connected device, Frida PS UA. In that list, one of the entries will be our target app, and Frida will tell us that a gadget is active inside it or not. When we see that gadget is activated, we type the second command, Frida UN gadget. So this attached Frida to the gadget. The U again means USB, and N gadget says attached to the process named gadget, which what our embedded gadget is called. Now we have a JavaScript REPL running inside the target app. We can write scripts that intercept function calls, dump memory, modify return values, and so on. For people who do not want to write Frida scripts from scratch, there is a tool called Objection. It's built on top of Frida and provides a nice interactive shell with a lot of pre-built commands. You can run it like this: Objection G, the name of the app and Explorer. And you get a prompt where you can type things like iOS keychain dump or SSL pinning bypass, etc. Finally, there's a tool called Grapefruit, which was previously known as Passionfruit. This is a comprehensive web-based analysis tool for iOS and Android apps. It gives you a graphical interface into the app, a browser for the sandbox, a class dumper, runtime inspection, and more. It's built on Frida, so it works the same way as Objection, but with a much prettier interface. And here is the GitLab link for this. So here we go, moving to the demo part, where we will see this main 3 attack vectors in action. The first one we will look at is data storage. On iOS apps, there are multiple data storage options. User defaults is the most basic one. Developers love it because it's very easy. It's just a keep value pairs, and it's stored in library preferences, bundle id.plist file. It's stored unencrypted, so it's not protected. If we will find any sensitive items stored in user defaults, that's certainly a finding. Then plist files, apps can generate their own plist files other than info.plist, so they may consider, they may store sensitive files there again, and that's not recommended at all because that's not encrypted. SQL databases, the same way, applications sometimes store structured data inside it. Which is not recommended because they are not encrypted as well. And keychain, which is the storage mechanism recommended for secrets. And this is also a SQL-like database stored in the application sandbox in this path. And but it's protected. It's encrypted database managed by iOS and recommended for storing small pieces of sensitive data. So let's see the demo of data storage. I will use Grapefruit for that. Let's start the video. As you see, we are starting the Grapefruit tool, its UI, and we are starting our target application, which is DVIA, which is a intentionally vulnerable application. We start it in the debug mode. And then we wait for the Grapefruit to connect to the application. We select our device in LLDB debugger. We list the processes. We find our application. We attach to it with its PID. And continuing. Then we will see our app listed here. We also have gadget, but we choose our main app, which is DVIA. As you see, we see the connected at the bottom, and the application also continues its execution. As you see, we can browse the application sandbox freely. This is done in a non-jailbroken device. The first one is storing some data in plist. We consider this is some sensitive information, username and password, and as you see, we can read this file from the sandbox. The second one is user defaults. Now the application will store the value we typed in the user defaults, secret 123, and we can access it in the path we talked about just a moment ago, libraries, preferences, and plist file. As you see, we found the value the application stored. So we can also analyze keychain storage of the application with Grapefruit. Then the second attack vector is authentication. with authentication. On iOS, we have LA Context API mainly used for biometric authentication, and the common method is evaluate policy, localize reason, reply, and this only returns true or false value, and most applications rely on the Boolean success callback to allow access. So it's possible to bypass authentication via hooking evaluate policy and force the callback to return true. And it's recommended to, but this is certainly not the secure way. And the recommended way is to protect sensitive data, let's say authentication token on your mobile application in keychain with a specific access control biometric bound, keysec access control biometry current set. So the OS itself enforces authentication via secure enclave, not just app logic. So let's see this in action here, authentication. We can easily hook into the API and we can return true, and the app will allow us. It's done here in the hooks. We activate biometric bypass. And on the vulnerable app, we tap on the Face ID button, as you see. Here, I click cancel, and you see it says authentication successful. Why? Because we hooked the API and returned true. That's it about authentication and network. This is fairly simple because this is all about requests being made to the backend. It's common with a lot of applications. So we can proxy this traffic. We can analyze it, requests and responses. Some apps, however, implement something called certificate pinning. This makes MITM attacks harder, but most of the time it can also be bypassed by hooking the pinning functions, because we have standard functions to implement this. And there are a lot of Frida scripts for this we can use to hook into those functions and always return like this certificate is fine. So the application will continue sending its requests to the backend server. We can see it in action here if time allows. The first one will be on Grapefruit. Grapefruit is great when it comes to analyzing network requests. We choose an SURL. I'm clearing the old requests and I start the logger. It will log all the requests I sent from the application, like HTTP and HTTPS, all of them. Grapefruit doesn't have SSL pinning bypass internally, but for this one I use Frida script I mentioned. So I connected to the gadget and I run the script. And I'm using Burp Suite as a proxy. Okay, I switched the interception on. We also need to configure the proxy configuration on our iOS device. We do this here. We enter the IP address and the port of our proxy. Okay. Okay. So we intercepted the request with SSL pinning here. That was all. Thank you for your attention. Yes. It was all for today. Thank you for your attention.